Hey guys, welcome back. This is going to be part one of the last video of the year for the study guide for the final. And it's going to include everything we did in the second semester. So if you remember, we started with work and energy and then moved on to momentum. Work is going to be equal to the force times the displacement, and they have to be parallel. Our potential energy was equal to the mass times the acceleration due to gravity times the height. Our spring energy is equal to 1/2 kx squared. And then we have kinetic energy, which is 1/2 mv squared. And then power is going to be work over time. And I wouldn't ask you guys to memorize any of the equations. They'd all be given to you. All right, so a 5 kilogram ball raised to 150 meters was the increase in potential energy of the ball. So this is our delta UG, and this is MGH. So I'm just going to take 5 kilograms times 10 meters per second squared, which is our acceleration due to gravity, times 150 meters. So this is going to give me 7,500 joules. Again, that's going to be the units for work for all of our energies. So that's going to be a Newton times a meter is what a joule is. If the ball is released and dropped, how fast would it be moving as it reached the ground? So if we're saying there's no air resistance, we're going to say that all of that potential energy would become kinetic energy. And we want to find out what speed it would achieve. So I would say that 7,500 joules would be equal to kinetic energy, which we're saying is 1/2 mv squared. So I'm going to multiply both sides by 2. I'm going to divide by the mass and square root. So in this case, our mass is 5. This is going to give us an answer that's a plus or minus, but because they ask us for the speed, which is a scalar, it can only be the positive answer. So gravity is a good way to store energy if you want to get it all back. So also are springs. So the spring above is stretched 0.3 meters by a mass of 0.5 kilograms. What is the spring force constant of spring? So we're asking for K. And our formula is that F of S is equal to Kx. Looking at our picture here, and really this is either the absolute value of these or it's negative Kx. This would be an F net equals 0. This block is just sitting here. So going down is the weight and going up is the spring force. So these two have to be equal to each other. That's our equilibrium. So F of S is going to be equal to mg. And so in this case, it's going to be 0.5 kilograms times 10 meters per second. So 0.5 times 10 is just going to give us 5 newtons. So if I get K by itself, I'm going to have that I have mg over x, which we said was 5 newtons, because that's what our spring force is when it's stretched this much, which was 0.3 meters. So our spring force constant K is going to be 16.7. All right, how much work did the block do in stretching the spring? That's going to be how much energy was put into and so I'm going to use my 1/2 K x squared formula. and I got 0.75 joules. All right, number 6, we have a power question. Power is just going to be work over time or energy over time. So in this case, our work is going to be our force times our distance. The force you would need to lift something would be equal to its weight. The distance it goes up would be equal to the height. So I'm going to have 500 kilograms times 10 meters per second squared times 40 meters divided by 60 seconds, which looks like it is 33,333 watts. All right, 7 and 8 are going to look at this picture. We have a cart that has 16 joules of energy. It's going to compress this spring. And so we're saying that it's traveling and it's going to compress it 0.5 meters. As it brings it to rest, I want to know what the spring force constant is. So all of this energy that was energy of motion is going to become energy stored in the spring, or 1/2 kx squared. So I want to get k by itself. I'm going to multiply both sides by 2. And then I'm going to divide by x squared. In this case, my x is 0.5 meters squared, and that's equal to k. So I have 2 times 16, which is 32, divided by 1/2, divided by 1/2. Which is going to give me 128. All right, it's then going to shoot it off and go up an incline and come to rest again. So now it's taken the spring energy, turned it into energy of motion, and now it's going to turn it into energy of gravity as it goes up. So we'd like to know how high it goes up. Well, I know that this is mgh. So I can set the 16 joules equal to mgh, and then just solve for h. So it's going to be 16 joules divided by the mass times the acceleration due to gravity. So we're saying the mass is 5, acceleration due to gravity is 10, and so the height, not how far it would go up the ramp, but the height it would go would be 0.32. All right, the very last section that we covered was E equals mc squared. We talked about nuclear energy. It can be fusion, where things combine. It can be fission, where things split apart. In both cases, a little bit of mass is lost, and that mass is turned directly into energy. And so this formula tells us that this change in mass, which they're telling us is 5.4 times 10 to the negative 29th kilograms, times the speed of light squared will tell us how much energy this is. And so this ends up being 4.86 times 10 to the negative 12 joules. So if we're talking about individual atoms, it's going to be a very small amount of mass lost and a very small amount of energy. All right, waves. Looking at our picture, they're asking us how many wavelengths are in this picture. And a wavelength is going to be a full cycle. So I'm going to say that's 1. Then it happens again to 2. And then we have another one, which is 3. It's really hard to read what this whole distance is, but we'll fill that in so it's clear to you guys. So this should be 1.5 times 10 to the negative 26 meters. So to find out what one wavelength is, we're going to say this is one wavelength, lowercase lambda. We're going to take the 1.5 times 10 to the negative 6 and divide it by 3. So I'm going to have 5 times 10 to the negative 7. All right, how many nodes and antinodes? So what are nodes? Nodes are the places where we're showing 0 energy. So we would have 1, 2, 3, 4, 5, 6, 7. Antinodes are places where we have maximum energy. So I have 1, 2, 3, 4, 5, 6. So those would have been the places on the candy bar where it was melted the most. All right, and then if the frequency of the wave is 3 times 10 to the third, what is the speed? So we're just going to take the frequency times the wavelength. So this is going to be 3 times 10 to the third hertz, and our wavelength is 5 times 10 to the negative 7th meters, which gives me 1.5 times 10 to the negative third meters per second. Very slow. All right, looking at 15, what point above is in phase with point C? Point C is at a node and it's going up, so E would also be. So when they're in phase, they're in the same part of the wave. We have 2 pulses going towards each other. When they meet, their resultant superposition will be a pulse of what amplitude? So I have one that is 0.8 and one that is 0.65. To add these together constructively, you just add them arithmetically, which just means you just add the 2 numbers together. That's all it means. So it's going to be 1.45 meters. Looks like I'm going to have to draw in a lens here. All right, an object is placed 10 centimeters from a lens with a focal length of 6 centimeters. Draw the ray diagram for the lens. All right, so it looks like my focal length, I'll make this and this 6. And I'm going to put my object at 10. All right, so the rules for this is that if this is a converging lens, which would be a convex lens, it's going to bring rays together. Every parallel ray is going to be bent through the far focal point. And then my second ray is going to go through the near focal point to halfway through and then get bent parallel. And where those cross is going to be where this part of the image is. So since I started at the top of the arrow, that's going to be where the top of my arrow is. So I would say that this is real. Why is it real? You get a real image if your rays actually cross and come together to make an image. And that's the case of what we're having right here. All right, we have light going from one medium to the other. They're telling us that the angle here is 50 degrees. So the angle here would be my angle of incidence, and that would be 40. Why? Because I know that this bigger angle here is 90. If this is 40, this is 40, and this is going to be my reflection. Why? That's the rules. When things reflect at a plane surface, they follow the law of reflection, and it's going to be the same angle in as the angle out. Some of the light can be bent, and this would be the angle of refraction. The index of refraction tells us how much this changes. This is going to be the speed of light divided by the speed in the new medium. So this is going to be 3 times 10 to the 8th divided by 2.4 times 10 to the 8th. And all of these index of refractions are going to be greater than 1. Air is almost 1, almost exactly 1. So this is going to end up being 1.25. So it's just a ratio of how fast it goes in nothing in a vacuum compared to how fast it goes through the new one. All right, so this works in Snell's law. Snell's law tells us that the first index of refraction times sine of our first angle is equal to our second index of refraction times the sine of our other. And we're saying that we have light that is hitting glass at an angle of 30 degrees. This is air, this is glass, and it's going to bend. And I want to know what that angle is in there. And since it's going from a lower index of refraction to a higher index of refraction, it's going to bend towards the normal. That's what happens. So I'm going to say that N1, which is going to be 1 because it's air, sine of theta 1 is going to be equal to N2 sine of theta 2. So if N1 is 1, we can just not worry about it. Now I want to know what sine of theta 2 is. So that's going to be sine of theta 1 over N2 is sine of theta 2. So theta is going to be equal to the sine inverse of sine of theta 1 over N2. The sine of 30 is 0.5. Again, you want to make sure your calculators are in degrees, right? So I'm not sure what you guys are doing in math. And then N2 we're saying is 1.33. So this should give me about 22 degrees when I put that in my calculator. So that's going to be the sine inverse. All right, on to electricity and magnetism. One metal ball has a charge of -4. Another metal ball has a charge of -10. They're going to be touched together. What's going to happen is that they're going to reach the same potential. So if we have a total of -14 charges, when they're brought together, then separated apart, they should each end up with the same if they're the same size and the same amount. So they're each going to end up with -7. All right, we have this Coulomb force, showed up in light as well, and it described what we had different energy levels for the electrons. It's equal to K Q1 Q2 over R squared. So we can find out what this force is. This Coulomb force is K Q1 Q2 over R squared. This K is a constant. It's 9 times 10 to the 9th Newton meter squared. Coulomb squared. I don't have enough room for that. And then I have Q1, that is 2 times 10 to the -4th. Q2 is -8. We don't put the negative in with this. This formula gives us the magnitude. And then we decide, are they the same charge and repel each other, or the opposite charges and they attract? So I'm going to put that in as a positive 8 times 10 to the -4th. And I'm going to put the distance between them in as 12 and square it. So this is going to end up being 10 newtons. What is the direction of the electric field from the combination of the charges? Electric fields go from positive to negative. So if I'm at P here, the electric field from A is going to be going that way. A small positive test charge would feel a force pushing it away from the positive one. The electric field from the negative one is also going to be to the right. A small positive test charge would feel a force pulling it towards the negative charge. So these are both going to the right. The combination of the two would make them to the right. All right, guys, I'm going to take a break here, and I'll come back with the second half of this at a later time.